Good morning, students. Unit 3, important unit. Each and every topic is important. There are 4 sessions are there. Each session is very important. Now, see, first one, this is the syllabus: diagonalization, eigenvectors and linear transformation, complex eigenvalues, application to differential equations, orthogonality and least squares, inner product, length and orthogonality, orthogonal sets. This is your syllabus. Now first one, diagonalization, eigenvectors and linear transformations. Now here the first one matrix is given to you. We have to verify whether the matrix is diagonalizable or not, right? This is very important topic. Now, if a matrix A can be factorized in the form of A is equal to P into D into P inverse, A is equal to P into D into P inverse, then the matrix is said to be diagonalizable. Simple, right? Now, see here the definition. Let A be a square matrix. A is said to be diagonalizable if A is similar to a diagonal matrix. That is, if A can be factorized as A is equal to P into D into P inverse for some invertible matrix P and for some diagonal matrix D. Right? When do you say that a matrix is diagonalizable? If it can be factorized in the form of P into D into P inverse. Right? Suppose now the first concept is, now one matrix is given to you. It is very easy to find the compute AK. If the given matrix is expressed in this form, then it is very easy to find A power K, and that is A square, A cube, A power 10, A power 20, A power 100, A power 200, right? Those values we can find very easily. Now where P is some invertible matrix and D is diagonal matrix. See here, when D is equal to 5003, it is of order 2 by 2. Now D square is D matrix into D matrix. This row into this column, 5 into 5 is 5 square, 0 into 0 is 0. Now this row into this column, 0 into 0 is 0, plus 3 into 3 is 3 square. If you simplify this one, D square is equal to, right? I am not writing this one as 25 and this one as 9. Simply I am writing 5 square, 0, 0, 3 square. Next we are computing D cube. D cube is can be written as D square into D. That means D square is this matrix, D is 5003. Once again, if you multiply these two matrices, you will get 5 cube 0, 0, 3 cube only. That means you can generalize this one. D power K is equal to 5 power K 0, 0, 3 power K for K greater than or equal to 1. Now definition of diagonalized matrix. Diagonalizable. A given square matrix is said to be diagonalizable if it can be factorized in the form of P, D, P inverse, where P is some invertible matrix, D is a diagonalized matrix D. See, the matrix A is said to be diagonalizable if and only if there is enough eigenvectors to form a basis of Rn. This basis A is a eigenvector basis. That point is very important. A matrix A is diagonalizable if and only if there are enough eigenvectors to form a basis of R power n. What is R power n, sir? That is collection of all n tuple forms a vector space, n tuple. This basis is a eigenvector basis. Next, the diagonalizable theorem, where A is an n by n matrix and is diagonalizable if and only if A has n linearly independent eigenvectors. A matrix is said to be diagonalizable if and only if it has n linearly independent eigenvectors. Let P is equal to P inverse with diagonal matrix if and only if the columns of P are n linearly independent eigenvectors of A. Right? The diagonal entries of D are eigenvalues of A that correspond respectively to eigenvalues in P. This is very important statement. Please go through the statement. This is very important statement. State and prove diagonalization theorem. They'll ask like this. Now, here A is an n by n matrix. It is a square matrix. If P, any n by n matrix with columns v1, v2 and so on vn, and if D is any diagonal matrix with diagonal entries lambda 1, lambda 2, lambda 3 and so on lambda n, then A into P is equal to, A is a given matrix of order n by n, where P is according to our assumption v1, v2 and so on vn. Now if you multiply this one, we are writing in a shortcut form the matrix AV1, AV2 and so on AVN. Now P into D, what is P? This matrix, right? B is nothing but v1, v2 and so on vn columns. D is what? Diagonal matrix. Diagonal matrix means lambda 1 0 and so on 0, 0 lambda 2 0, so on and 0 0 and so on lambda n, where D is a diagonal matrix whose entries are lambda 1, lambda 2, lambda 3 and so on. Here the statement. Now if you multiply this one, what you will get? P. What is P actually? v1, v2 and so on vn. That means lambda 1 into v1, lambda 2 into v2, lambda n into vn only. Because there is only one row in the matrix P. That means each one is a column vector here, remember. Now, suppose A is diagonalizable. This is our assumption. That means A can be written as PDP inverse. A is equal to PDP inverse. Both sides post multiplying. This is post, not past. Post multiplying by P. A into P is equal to PD, P inverse into P. AP is equal to PD into P inverse into P. That means P is a matrix. We are multiplying a matrix by its inverse of the matrix. Inverse. Then we will get the identity matrix. That identity matrix is nothing but I. That means A into A inverse is I, no? Like that P inverse into P is I. AP is equal to PD into I. AP is equal to PD. AP is what? A1 V1 comma AV2 AV1 comma AV2 comma so on AVN. From here, what is PD? That is lambda 1 into V or V lambda 1, both are same, right? Lambda 1 V, lambda 2 into V2 and so on lambda n into Vn. Comparing line coefficients, AV1 is equal to lambda 1 V1, AV2 is equal to lambda 2 V2, AVN is equal to lambda n Vn, right? Now, since the matrix P is invertible, its columns v1, v2 and so on vn must be linearly independent, and also since these columns are non-zero according to our assumption, because from the statement we are getting this one. From 1, lambda 1, lambda 2 and so on lambda n are eigenvalues, and v1, v2 and so on vn are corresponding eigenvectors. What is equation 1 are? Equation 1 is a1 in av1 is equal to lambda 1 v1. This is in the form of what? Ax is equal to lambda x, right? If Ax is equal to lambda x, lambda is said to be an eigenvalue and x is said to be an eigenvector. Here see, a v1 is equal to lambda 1 v1. That means lambda 1 is called an eigenvalue and v1 is said to be an eigenvector. Similarly in this case also. Now we are comparing that one with the general statement. If Ax is equal to lambda x, lambda is said to be an eigenvalue and x is said to be its corresponding eigenvector. That's why from equation 1, lambda 1, lambda 2 and so on lambda n are eigenvalues, and v1, v2 and so on vn are called corresponding eigenvectors. What is the converse? Converse is, for any given n eigenvectors v1, v2 and so on vn, by using these eigenvectors, construct the columns of P and use corresponding eigenvalues lambda 1, lambda 2 and so on lambda n to construct D, right? See, AP, therefore AP is equal to PD. The eigenvalues are linearly independent and the P, therefore P is invertible by the definition. If the eigenvalues are linearly independent, eigenvectors are linearly independent, then P is invertible. That is AP is equal to PD. Since P is invertible means inverse of a matrix exists, right? Where both sides we are multiplying by P inverse. AP P inverse is equal to PD P inverse. P into P inverse is equal to I. Now A into I is I, where I is a unit matrix. Therefore A is equal to PD P inverse. Now here please go through this statement. These statements are very, very important. This one and this one and this one are important, right? Next one. problems. Let A is equal to matrix 7 2 minus 4 1 2 by 2 matrix. Find formula for AK given that A is equal to PD P inverse, where P is equal to this one and D is equal to this matrix. Given that A is equal to 7 2 minus 4 1 2 by 2 matrix, P is also 2 by 2 matrix, D is equal to 5 0 0 3, and A is equal to given as P D P inverse. Now here P is equal to 1 1 minus 1 2, therefore P inverse is equal to 2 1 minus 1 minus 2. How to find inverse or means? That means it is of order 2 by 2. If A is equal to ABCD, then A inverse is equal to 1 by AD minus BC into D minus B A minus C A. Right? Consider A square is equal to A into A. A square is equal to A means what? By given hypothesis PD P inverse. Again A is equal to PD P inverse. Open the brackets. P inverse into P is equal to I. D into I is I. PD D P inverse. D into D is D square. P D square P inverse, which is nothing but A square. Therefore A square is equal to P D square P inverse. A cube is equal to A inverse into A. A square into A, where A square is this one. A is again given data P D P inverse. P D square P inverse into P D P inverse is equal that means if you multiply these two, again you will get an unit matrix, right? D square into I is D square only. D square into D is D cube. Therefore A cube is equal to P D cube P inverse. In general, A power K is equal to P into D power K into P power minus 1, where A power K is equal to, what is the value of P? 1 1 minus 1 minus 2, and D power K is 5 power K 0 0 3 power K, and P inverse value is from here 2 1 minus 1 1. If you multiply all these things, you will get this result. A power K is equal to this matrix. Next one, diagonalize the matrix A if possible. Is important concept. In this unit everything is important. Diagonalize the matrix A 1 3 3 minus 3 minus 5 minus 3 3 3 1. Possible if possible. Given matrix, see this is very important. Given matrix is this one. We have to find an invertible matrix P and a diagonal matrix D such that A is equal to P D P inverse. This can be done in 4 steps. The step 1, first of all we need to find a characteristic values, right? A minus lambda I. To find the characteristic values or eigenvalues, we need to find A minus lambda I. A minus lambda into unit matrix. Why you are taking 3 by 3 matrix means because the given matrix is of order 3 by 3. A minus lambda I is equal to this one. To get the characteristic values, we have to find the characteristic equation, right? This is the characteristic equation. We are expanding the determinant, we are equating it to 0. Therefore, the characteristic values are 1 minus 2 minus 2. These are also known as eigen values. For step 1, we found characteristic values, or you can say eigen values, right? Now, see. Eigenvalues are 1 minus 2 and minus 2. Step 2, we need to find its corresponding eigenvectors. This step is very important. Find a linearly independent eigenvectors of A. Since A is of 3 by 3 matrix, these vectors are needed. This is a critical step. If it fails, by the theorem, A cannot be diagonalized. That means if you won't get the eigenvectors, corresponding eigenvectors linearly independent, then A cannot be diagonalized. Therefore, for lambda is equal to 1, how to find the corresponding eigenvector? See, if lambda is equal to 1, A minus lambda into x is equal to 0. Lambda is 1, A minus 1 into I into x is equal to 0. A minus 1i, that means unit matrix. Simply you are subtracting A minus lambda I. 0 3 0 minus 3 minus 6 minus 3 3 3 0 into x is x1 x2 x3. Because it is of order 3 by 3, therefore we have to take a column matrix x1, x2, x3 and equate it to null matrix 0, 0, 0. Now multiply this one, 0 into x1 plus 3 into x2 plus 3 into x3 is equal to 0, minus 3 into x1 minus 6 into x2 minus 3 into x3 is equal to 0, 3 into x1 plus 3 into x2, 0 into x3 is equal to 0. If you solve this one, x1 is equal to x3 and x2 is equal to minus x3. Therefore, the eigenvector is v1 is equal to x1, x2, x3 means what is x1 say, assuming that x3 is equal to 1 aite, if assume that x3 is equal to 1, in that case x1 is equal to 1 and x2 is equal to minus 1. Similarly, when lambda is equal to minus 2, we need to find characteristic eigen or a characteristic vector, or you can say eigenvector. A minus 2i into x is equal to 0. The corresponding eigenvector, if you simplify this one, you will get this v2 as minus 1, 1, 0. If lambda 2 is minus 2, another case, because there are 3 eigenvalues are there, or you can say characteristic roots are there. That means we need to find 3 eigenvectors, or you can say characteristic vectors. Once again, if you repeat this one, again v3 is equal to minus 1, 0, 1. It depends upon the procedure, right? Now the solving procedure. Now the set v1, v2, v3 is linearly independent. This is v1, v2 and v3. These are linearly independent. In step 1, we have to find the characteristic values. In the second step, we have to find the characteristic vectors. In step 3, construct the P, the matrix P using step 2. That is P is equal to v1, v2, v3 according to the theorem, right? Column vectors we have to write. What is P1? V1, 1 minus 1, 1. V2 is minus 1, 1, 0. V3 is minus 1, 0, 1. Right? Here order is not important. That is not immaterial. Now, step 4, after getting P using step 2, step 4, construct D from the corresponding eigenvalues. D is always a diagonal matrix whose entries, the principal diagonal entries are characteristic values only. Here what are the characteristic values? 1, minus 2, minus 2. Therefore D is equal to 1, 0, 0, 0, minus 2, 0, 0, 0, minus 2. Therefore A is equal to P into D into P inverse. Right. No need to multiply all these 3 matrices. If you want to cross check that one, hint is find AP and PD. If you multiply AP and PD, both are equal to this one. See, PD is equal to say this matrix and AP is equal to this matrix. That means A is equal to P into D into P inverse. No need to find P inverse for 3 by 3 matrices. Right? Simply you can use this step. Next, it's a homework for you. Diagonalize the matrix A if possible. Now you have to follow those 4 steps. In the first step, we have to find the characteristic values or eigen values. In the second step, we need to find the corresponding eigen vectors, or you can say characteristic vectors. In step 3, we have to construct the matrix P. Step 4, you have to write the diagonal matrix using the eigen values. And the last conclusion is this one. A is equal to PD P inverse after this verification. Now, next one. An n by n matrix with n distinct eigenvalues is diagonalizable. It's a theorem. Let A be an n by n matrix, that is a square matrix. Let lambda 1, lambda 2 and so on lambda n be the n distinct eigenvalues. Right? N distinct eigenvalues. Let v1, v2 and so on vn be the eigenvectors. If lambda 1 is an eigenvalue, its corresponding eigenvector is denoted by say v1. If lambda 2 is the eigenvalue, then its corresponding eigenvector is denoted by v2 and so on. Corresponding to n distinct eigenvalues of lambda 1, lambda 2 and so on lambda n of the matrix A. Then v1, v2 and so on vn. This collection is always linearly independent. Therefore, hence A is diagonalizable. Next, let A be an n by n matrix whose distinct eigenvalues are lambda 1, lambda 2 and so on lambda p. For 1 less than or equal to k less than or equal to p, the dimension of eigenspace for lambda k is less than or equal to the multiplicity of the eigenvalue lambda k. Important concept. Now, the I matrix A is diagonalizable if and only if the sum of the dimensions of the distinct eigenspaces equals n, and this happens if and only if the dimension of the eigenspace for each lambda I equals to the multiplicity of lambda k. And the third point is, if A is diagonalizable and Bk is the basis for the eigenspace corresponding to lambda k for each k, then the total collection of the vectors in the sets b1 and so on bp forms an eigenvector for the basis r power n. These are the points you have to remember. You have to by heart. This first point is very, very important. Right? This will we are going to use this concept in problems. The next one is diagonalize the matrix A if possible. Right? See, I'll explain this problem in the next video.